Hello, everyone. I'm Tejas, and I'm here to present our work on rotation synchronization via deep matrix factorization. This work has been jointly done along with Giacomo Zara, Paolo Rota, Andrea Fusciello, Elisa Ricci, and Federica Arrigoni. In this paper, we address the rotation synchronization problem, where the task is to recover absolute rotations starting from the pairwise ones. Rotation synchronization has a wide range of applications in computer vision, with the most prominent ones being 3D point cloud registration, post-graph optimization, and structure from motion. Let's look into more deeply on what rotation synchronization is about. Rotation synchronization is an instance of the more general synchronization problem, where the task is to find elements of a group starting from pairwise ratios. In our work, we are concerned about the special orthogonal group, whose elements are rotations in the 3D space. So, given an input, a set of relative rotations, the task is to compute a set of absolute rotations such that the following constraint equation is satisfied. The existing works can be divided into two parts: traditional methods and deep learning methods. Traditional works involve optimizing a cost function using methods like linear least squares, iterative methods, and etc. The more recent deep learning-based methods are based on graph neural networks. However, this approach has its own limitations, that being all these approaches are supervised and need a large data set to train with. With this factor being a motivation, we propose a novel deep learning-based method that is unsupervised. We view this task as a matrix completion problem and address it via deep matrix factorization. In our approach, we have a partial matrix which contains observed-related rotations. Our objective is to find the complete matrix with the missing observations and at the same time denoising the observed rotations as well. Hence, this can be viewed as a matrix completion problem. So given a sampling set, the task is to find a complete matrix W that is as close as possible to the input partial matrix on the set of available entries. There exist many solutions to this problem, the most common being introducing some kind of explicit regularization. In our approach, by applying gradient descent on a matrix factorization, we induce an implicit regularization, which tends to produce low-rank solutions. And finally, to optimize the solution, we substitute the L2 norm, typically used for deep matrix factorization, with the L1 norm, motivated by the fact that the L1 is more robust to outliers than the former. Unlike traditional neural models, where an input corresponds to a predicted output, a solution regresses the complete matrix starting from a randomly initialized matrix of equal dimensions. Our network, named DMF-Sync, is implemented on PyTorch as a plain sequence of linear layers. The forward pass during the training involves computing a matrix from the product of several different matrices, which here corresponds to the linear layer itself. After the first iteration, at every iteration, the input matrix is obtained by transposing the weights of the first layer, hence reducing the input noise variability. At training time, the reconstructed matrix is compared with the incomplete matrix for backpropagation, and for evaluation, it is compared with the complete ground truth. So now let's take a look at some of the properties our approach exhibits. Our approach is unsupervised, hence doesn't require any kind of external training data to learn from. We can say that our approach follows a single scene setup, whereas previous deep methods perform learning from multiple scenes. Our method is based on deep matrix factorization, implemented using linear layers, hence making it more interpretable. By applying a gradient descent-based optimization on deep matrix factorization, we introduce an implicit regularization and tend to produce low-rank solutions. We report experiments on both synthetic data, where we validate some properties of DMF-Sync, and real data, where we compare our approach to the state of the art. In the case of synthetic data, results show us that for two different node scenarios, increasing the depth led to more accurate solutions. This also verifies that L1 norm, when combined with deep matrix factorization and gradient descent, induces an implicit regularization in our network. For the real data, we consider the 1DSFM benchmark and compare our methods with other deep learning based approaches and the traditional method. Recall that our approach is unsupervised, hence, it works with weaker assumptions than previous deep methods. It can be seen that our approach has comparable accuracies to other relevant methods in many cases. So, to summarize, in this paper, we have presented an unsupervised approach for the rotation synchronization via deep matrix factorization. This formalization helps our approach to exhibit implicit regularization and reaches comparable accuracies while working under weaker assumptions. Our code is available online on GitHub. Thank you for your attention.